The basic recipes cover most kitchens, but some problems need specialized techniques. And every single recipe, no matter how it was built, needs quality control. This is where the head chef earns their title. 3 kitchen stations running simultaneously. Japanese, transcriptomics. Italian, proteomics. French, metabolomics. Essential regression takes dishes from all 3 and finds the hidden flavor profiles that connect them. These latent factors capture the shared biology across data types. Unlike LASSO, which picks individual ingredients, essential regression discovers the underlying structure linking multiple measurements to the same outcome. In multi-omics integration, it often outperforms single dataset methods because it exploits what the datasets have in common. A grandmother, a mother, and a daughter, all chefs. Their dishes taste similar. But is it because they use the same ingredients or because they inherited the same recipe book? Phylogenetic generalized least squares corrects for shared ancestry before testing whether an ingredient truly matters. Without this correction, you'd conclude all Italian grandmothers' dishes are similar because of olive oil when really it's a family tradition. In comparative biology, PGLS accounts for evolutionary relatedness when modeling trait correlations across species. The recipe is finalized, but does it work on dishes you haven't tasted? Split your data into 5 groups. Train on 4, test on the 5th. Rotate 5 times so every dish gets a turn as a blind test. If the recipe works well on all 5 holdout groups, it generalizes. If it only works on the dishes it was trained on, it memorized rather than learned. This is cross-validation, and it's how you estimate whether your 20,000 gene model will survive the next patient cohort. 2 competing recipes on the podium. Recipe A uses 3 ingredients and scores 90. Recipe B uses 30 ingredients and scores 92. Which is better? Ake and Big give the Simplicity Award. Both penalize complexity. More ingredients cost you points. Big penalizes harder, demanding justification for every additional ingredient. The winning recipe balances accuracy and parsimony. In model selection, this prevents you from fitting noise with an over-engineered 500 gene signature when 10 genes would do. One final quality check. After building the recipe, inspect the scraps, the residuals. These are the differences between what the model predicted and what actually happened. If the scraps scatter randomly, the recipe captured the real pattern. If they curve, you missed a nonlinear relationship. If they fan out, your precision depends on the input level. Every good regression analysis ends by looking at the leftovers. 16 regression methods. 3 evaluation tools. 1 recipe lab. Trummels to random forest. Every method is just a different strategy for cracking the recipe. Know your outcome. Know your ingredients. And the right method follows. Thank you for visiting the Recipe Lab.